The Lexicon prefix-tree router is a monotone routing substrate designed for hierarchical path resolution in distributed key-value environments. The core architecture maintains a persistent trie structure where each node stores a routing table mapping prefix segments to downstream node identifiers. All operations execute with deterministic latency bounds. The system initializes with a root node containing a default route designation. Nodes are immutable once committed to the primary storage layer. Prefix insertion operates through a sequential traversal mechanism. When a new prefix arrives, the system walks the existing trie from root, comparing input bytes against stored segment boundaries. At the first mismatch point, a new internal node is created and the remaining prefix chain is appended. The insertion process does not trigger rebalancing. All nodes maintain insertion order timestamps in milliseconds since epoch for audit purposes. The lookup operation begins at the root node and proceeds depth first through the trie structure. At each level, the system compares the input key against stored segment prefixes using memp semantics. When a complete prefix match is found, the routing table entry at that node is consulted. If no exact match exists, the system returns the routing entry from the longest matched prefix. This behavior implements longest prefix match semantics. Route table entries contain 4 mandatory fields. Target node identifier is a 64-bit unsigned integer, priority value ranging from 0 to 255, TTL in seconds, and cost metric as a 32-bit value. The routing decision mechanism selects the entry with highest priority among all matching prefixes at the final traversed node. In case of priority ties, cost metric determines selection. TTL expiration is checked at query time without background eviction. Segment compression reduces memory overhead through prefix aggregation. When a node contains a single child, the parent-child segments may be merged into a single combined segment. This operation preserves routing semantics while reducing heap allocations. Compressed segments store the full byte sequence with no padding. Decompression is transparent to the query path. Compression decisions are made during offline batch processing phases only. The split operation divides a trie node when its routing table exceeds capacity thresholds. The system selects a median segment prefix and creates 2 child nodes. All entries are redistributed into the appropriate child based on prefix ordering. The parent node maintains 1 route entry pointing to a dispatch node. Split operations occur asynchronously during maintenance windows. The router remains operational during splits through lock-free read mechanisms. Edge cases in prefix matching include zero-length prefixes, which resolve to the root node entry. Wildcard patterns are not supported in the core implementation. When input length exceeds the trie depth, the system terminates at the deepest matched prefix. Queries with null or invalid node identifiers return an error code. The system does not perform automatic prefix normalization or canonicalization. Memory layout for internal trie nodes follows a fixed structure. The first 8 bytes store a generation counter and node status flags. The next 16 bytes contain parent node reference and segment offset within parent. Following that is a 256-entry jump table for byte value optimization. The remainder holds variable length segment data and routing entries. All numeric fields use little endian byte ordering. Persistence is handled through append-only write-ahead logging. Before any trie modification, a log entry is written containing the operation type, affected node identifier, and new state. Log entries are flushed to disk with fdata sync semantics. Recovery after unclean shutdown replays the log sequentially. The system maintains 2 log files to prevent corruption during rotation. Log files are pruned when checkpoint markers are written. The eviction policy operates on unused route entries during maintenance phases. Entries with expired TTL values are marked for deletion. The system maintains reference counts for each route entry. When reference count reaches 0 and TTL expires, the entry may be reclaimed. Deletion does not trigger immediate node restructuring. Orphaned leaf nodes are cleaned up during offline compaction operations. Concurrent access is controlled through reader-writer lock semantics. Multiple readers may traverse the trie simultaneously without blocking. Write operations acquire exclusive locks at the node level. Lock acquisition uses exponential backoff if contention is detected. Deadlock prevention is ensured through strict hierarchical lock ordering by node depth. Lock timeouts are configurable and default to 5 seconds. Monitoring and telemetry are collected through an instrumentation layer. Each node tracks lookup count, insertion count, and average traversal depth. Route entries record hit counts and last access timestamp. These metrics are aggregated at 5-minute intervals. The system exports metrics in a simple text format compatible with standard collection systems. Telemetry collection has negligible performance impact. Configuration parameters control runtime behavior through a flat key value store. The parameter max node routes limits routing entries per node, defaulting to 256. The parameter compression threshold triggers merging when a node has fewer than 4 children. The parameter split factor controls the split operation granularity, set to 1024 entries. All parameters are immutable at runtime and must be set before initialization. Backup and recovery procedures involve periodic snapshots of the entire trie structure. Snapshots are written in a binary format including all node metadata and routing entries. The snapshot format includes a header with version number and checksum. During recovery, snapshots are validated before loading. Incremental snapshots contain only changed nodes since the previous full snapshot. Snapshot creation does not block normal router operations. Error handling follows a simple code-based system, where 0 indicates success and non-zero codes represent failure categories. Code 1 indicates prefix not found. Code 2 indicates invalid routing entry. Code 3 indicates lock acquisition timeout. Code 4 indicates persistence layer failure. All error codes are documented in the client library header files. The system never raises exceptions for runtime errors. Performance characteristics for typical operations are as follows. Lookup latency is O of log n, where n is the total number of prefixes. Insertion latency is similarly O of log n plus the length of the prefix. Route updates occur in constant time. Memory usage grows linearly with prefix count and segment length. These characteristics remain stable across load variations. Detailed benchmarks are provided in the appendix.